All right, welcome everybody. Today we're going to talk about lesson number 21, which is section 2.6, and this is an introduction to rational functions. We're going to talk about how would you identify restricted values, how would you find the domain, and how would you find the intercepts. So because of the fact that the graphical component is so important in these next couple of lessons, it's possible that we're going to see them all in this format using notes and the class notebook as opposed to a PowerPoint, because it is important that you write down all the information and that you have the graphs to look at. So here in the first example, consider the rational function 2x squared minus 5x minus 3 divided by x squared minus x minus 6. Now, just to be clear, the reason why this is considered to be a rational function is because there are polynomials on both the top and the bottom. Up until this point, we've only been asked to graph one or the other, and now when we're asked to graph a ratio of polynomials, that's what makes a rational function. So if this is the f of x function and they're asking you for f of 0, then that of course means that everywhere there's an x, you're going to put a 0. So that's going to give you 2 times 0 squared minus 5 times 0 minus 3 all over 0 squared minus 0 minus 6. If you go ahead and start to simplify, you can see that any term that has a 0 in it is going to cancel, giving you negative 3 over negative 6, which means you are going to get an answer of positive 1/2. If you go ahead and calculate f of negative 2, that's going to give you 2 times negative 2 squared is 4, minus 5 times negative 2 minus 3, all over, again, negative 2 squared is 4, minus negative 2 is going to be plus 2, minus 6. If you go ahead and calculate the top, 8 plus 10 minus 3 is 15. On the bottom, you're going to get 6 minus 6, which is going to give you a 0. And hopefully you remember that if you get anything divided by 0, as far as we're concerned, that's undefined. For f of 3, that's going to give you 2 times 3 squared is 9, minus 5 times 3 is 15, minus 3, all over 9 minus 3 minus 6. In the numerator, that's going to give you 18 minus 18, which is 0. In the denominator, you're also going to get 0. And when you get 0 over 0, that is also undefined. Just to kind of hit you with a little bit of a calculus term, that's actually what's called the indeterminate form, which means we can't determine a lot of things. But again, as far as we're concerned, f of 3 would be undefined. So we're kind of interested as to what values give you actual numbers like f of 0, as opposed to those that give you undefined. So in order to kind of take that information and do more with it, we're going to start by taking the f of x function and we're going to go ahead and write it in factored form. So if we take our polynomial and we factor the numerator and the denominator is obviously easier to factor, factors of negative 6 that add up to be negative 1. That would be x plus 2 and x minus 3. When it comes to the numerator, if you were going to factor this, you have a couple of different ways. Some of you guys can just factor it old school by looking at it. You may have to use the AC method, or honestly, at this point in your math careers, you probably have come up with some method that works. But regardless, you should be able to factor it as 2x plus 1 and then x minus 3. So again, this is what's called factored form because both the top and the bottom are factored. So it asks you, what do you notice about the results of 2 of the 3 functions and the factored equation? Well, hopefully you can notice here the fact that f of negative 2 and the fact that f of 3 were where the undefineds were. Those are relevant because those are the values that are in our denominator. So if we kind of want to summarize that, when factors of the denominator are set equal to 0 and solved, the results, x equals negative 2 and x equals 3, are x values that cause f of x to be undefined And again, that's kind of, a wordy way of saying it. You probably are going to remember a fair amount of this from last year. But because of the fact that we do want to start explaining and writing in full sentences, keeping our eye on the free response questions we're going to have to answer on the AP test next year, it is kind of good just to start writing things out longhand from time to time. So again, when factors of the denominator are set equal to 0 and solved, the results that you get for those x's are x values that cause f of x to be undefined. So then they ask you again for the definition of a restricted value. So it's not all that dissimilar, but we're trying to just, again, get our kind of, English bone working along here with our math bone. So basically a restricted value is a value of x for which there is no y value. If for a rational function, these are anything that make the denominator 0. And obviously I like to abbreviate, so hopefully you're fine with that. And again, a definition of a restricted value. Whoops. A restricted value is a value of x for which there is no y value, and in a rational function, they always come from the denominator. So if we take a look at this first rational function right here, f of x, again, it's the same picture. We're going to go ahead and describe the graph at its two restricted values. So the two values in question are x equals -2 and x equals 3. So hopefully you would notice that here at x equals -2, that is what we would call a vertical asymptote. And then here at 3, that is a hole or an open circle. We have started referring to them in the past previous lessons as discontinuities. So there was a reason we were kind of setting ourselves up for this. So at x equals -2, remember that is what we would call an infinite discontinuity. And at x equals 3, that is what we would call a point discontinuity. We're going to talk a little bit more about discontinuities tomorrow. And then in terms of what is the domain of the function graph, well, again, hopefully you remember from earlier lessons that a function is continuous everywhere except where the discontinuities are. So if you assume that the domain starts at being all real numbers, which means you would start at -infinity, you would take a break at the first discontinuity, which would be -2. Then you would be good between discontinuities, and then you would take a break at the second discontinuity, which would be 3. So again, everything we do has a purpose. We're kind of trying to bring in these calculus topics, of which being a discontinuity and not being continuous is something that is really quite important. So now, notice that on the next page, I have given you the graph of 4 rational functions, and I want you to describe to me some of the ways that they are the same, and then some of the ways that they are different. And then we're going to kind of formalize the process here. So take a look not only at the graphs, but also at the equations. Some things you might want to notice. So notice the fact that each of these problems has a quadratic on the top and a quadratic on the bottom. So think about how the graph might look different if there was a larger degree on the top versus if there was a larger degree on the bottom. So as you look at these 4 pictures, and again, you try to identify some things that are in fact different, we'll kind of just highlight them here, and then I'll formalize them up on the top. So notice they're called F, H, G, and P. So the first thing that we notice about H, notice how there are 2 vertical asymptotes, as opposed to all the other ones only have 1. Something else to notice is that h of x does not have any point discontinuities where the other graphs do. So there's a point discontinuity in each of these 3, but there isn't one in h of x. Notice that when it comes to horizontal asymptotes, which are the ones that go left to right, notice that for this graph here, the graph crosses that horizontal asymptote where it does not cross in the other ones. Notice that again in h of x, there are 1, 2, 3 pieces to the graph, whereas in all the other cases, there are only 2 pieces. And finally, notice that again for h of x, there are 2 different places where the graph crosses the x-axis. Those are, of course, the zeros. Compare that to the other functions where they all have just 1 each. So good that you're kind of getting used to what the graphs look like. Again, because of the fact that there are so many multiple choice questions on the AP test, it's very likely that they will give the graph to you and then ask you questions about it. So again, we kind of already talked about it, but let's just summarize the 5 different ways that one of the functions is different than the others. So we're talking about h of x has 2 vertical asymptotes, where all the rest only have 1. Again, for number 2, h of x has no point discontinuity. The third thing is h of x crosses the horizontal asymptote, which I'm going to call an HA for short. H of x has 3 pieces compared to the other functions that only have 2. And then finally, h of x has 2 zeros compared to the fact that the other ones all just have 1. So I thought this was kind of a good way to remind you of what it meant to be a rational function, remind you of all the different ways that they can look. And again, they are going to get more complicated as the lessons progress, but because this is just the first day, we don't see anything too crazy. And again, hopefully you remember that asymptotes are generally drawn with dashed lines. You can also draw them with a highlighter if you would prefer. So we're going to kind of try to take all that information that we found previously and kind of try to organize it nicely, which is why I have this table for you. So notice that these 4 equations are the same equations that we saw the graphs of previously. And now we're going to kind of find all the important information and then hopefully be able to realize why each graph looks exactly the way that it does. So we're going to go ahead and start by factoring everything in sight. So here for the first one, we're going to factor the top as the difference of squares. And then we're going to factor the bottom by taking out just a greatest common factor, which would be 2x. And that's going to give us x plus 6. Then here in the one below it, factors of negative 6 that add up to be negative 1. That's going to be x plus 2 and x minus 3. Factors of negative 10 that add up to be positive 3. That's going to be plus 5 and minus 2. Then the one below it, again, for the numerator, you would factor that using any method that you have used over the years. For me, I'm just able to kind of look at it and know what the answers are. You could do as much or as little work as you might need to. So AC method potentially on top, and then difference of squares on the bottom. For the last one, factors of 3 that add up to be 4, that would be positive 1 and positive 3. In the denominator, that would be x plus 3 and x minus 1. So nothing here on the first day is really too difficult in terms of the factoring. Obviously, that can bump up significantly as the days progress. So you're certainly going to want to make sure that you review this easy factoring if you don't already know it. So not only did it want you to factor completely, but it also wanted you to write the restricted values. So I kind of ran out of room in my box. So you can either write them in the box or I'm just going to write them over here on the left. So basically, x cannot equal anything that would make the denominator 0, which in example 1 would be 0 and negative 6. How am I getting these? Well, these are, of course, anything that make the denominator 0. So negative 5 and positive 2. In the third one, x cannot equal negative 1 or positive 1. And for the last one, x cannot equal negative 3 or positive 1. So again, we're kind of just laying the foundation for the harder things that are to come, making sure that you remember how to factor and making sure that now after seeing a couple of examples, you know that the restricted values are anything that makes the denominator 0, which is why it's so important that you factor first, because then it's super easy to see. When it comes to the domain, okay, we can go back and look at the graph if we need to, but if we just think about what it means for a graph to be continuous, a graph is generally continuous from negative infinity to infinity, except for anywhere that there's a discontinuity. So we're going to go ahead and write each of these domains, breaking for discontinuities. So if you're watching this on your own, maybe pause and try it and go ahead and see if you can write all 4 of those domains. I'm going to go ahead and write them as well. So if you're watching it together, you can try to pause and try it as well, keeping in mind that we're looking at the denominator. So negative infinity, then to the first discontinuity, which is -6, -6 to 0, and then followed by 0 to infinity. Again, you have to break for all kinds of discontinuities. Then for the next one, negative infinity to the first break, which is -5, -5 to the second break, and then the second break to infinity. Negative infinity to -1, -1 to 1, and 1 to infinity. And then finally, negative infinity to -3, -3 to 1, and 1 to infinity. So again, trying to make connections between the old stuff and the new stuff. Being a restricted value means there's a discontinuity, which means that the function is not continuous there, which of course means that there's a domain restriction. In the next box, it's asking you to set each of the non-canceling factors of the numerator equal to 0. So non-canceling factors means that there can't be a common factor in the denominator because that means something different. So here in the first one, the non-canceling factor is x minus 6, which of course then if you solve, you're going to get 6. In number 2, you have 2 non-canceling factors. So if you solve the first one, you're going to get -2. If you solve the second one, you're going to get 3. In the next one, the non-canceling factor is 2x minus 5. And if you set that equal to 0 and solve, you're going to get 5/2, which is, of course, 2.5 if you prefer. And then finally, for the last one, if you set the non-canceling factor, that's x plus 1, which is going to give you an answer of -1. When it asks you what are the zeros of the function according to the graph, so the zeros are going to be anything that you found in the previous step, which of course, another word for 0 is an x-intercept. So if we were to go back and look at our graphs, anywhere there's a red dot, those values should match up exactly with the values that we found here, which of course they do. So the 0 here would be 6. Here there would be 2 of them, -2 and 3, 5/2, and -1. What is the value of the constant term of the numerator over the constant term of the denominator? So the constant terms are, of course, anything that doesn't have a variable, and you're going to want to be careful just to make sure that you're looking at the right thing. So in the first one, the constant term of the numerator is -36 divided by the constant term of the denominator, for which there is nothing. A 0 on the bottom, as far as we're concerned, is undefined. In the next one, you're going to get -6 over -10, which reduces to be 3/5. Write that a little bit nicer. If you haven't noticed, I got a nice new fancy pen for my Surface, so hopefully things are a little bit neater than they've been. Here in the next one, you're going to get -5 divided by -1, which is going to give you a +5. And then in the last one, you're going to get 3 divided by -3, which is going to give you -1. When they ask you what are the coordinates of the y-intercept, well, to find the y-intercept, hopefully you remember that you're going to set the x equal to 0. If you set all the x's equal to 0, turns out that all you're going to be left with is the constant on the top and the bottom. So really what you found in the previous column is giving you the y-intercept. For a value that's undefined, that means there is no y-intercept. The graph will never cross the y-axis. Whereas in the second one, you would have 0, 3/5, followed by 0, 5, and 0, -1. 1. So even if you remember all these rules from last year, it certainly doesn't hurt to kind of get a better explanation. Again, the chances that you're going to be asked to graph from scratch, either this year because of the technology limitations or on an AP test because of the fact that it's multiple choice, it's more likely that you're going to be asked to analyze a graph or analyze an equation. So hopefully setting it up this way is going to help you do that a little bit better. And now finally on to the last page here, we're going to kind of just go ahead and take all the information that we found so far, summarize it. That way when you go to do your homework and when you go to do the lessons that are upcoming, it should all be nice and simple. So in the first one, from the equation of the rational function, how do you determine the restricted values? From the second one, we're looking for domain, zeros, and y-intercept. So I want to just make sure that I'm highlighting the important stuff. So if you want to find the restricted values, you are going to set factors of the denominator equal to 0 and then solve for x. And again, I like to abbreviate, so hopefully you can follow. So set factors of the denominator equal to 0 and solve for x. How do you find the domain? So you basically start with negative infinity to infinity and exclude the restricted values. And those are, of course, the discontinuities. How do you find the zeros? So you're going to set a non-canceling factor of the numerator equal to 0 and solve for x. And then how do you find the y-intercept? So the easy way that we always do is, of course, you set equal to 0. But from a rational function, it's the ratio of the constant terms of the numerator and the denominator. So all that's doing is formalizing everything we just did in the notes, but I don't think that it could hurt to have it all written out. So how are you now going to apply that information both in this example and tonight? The first thing you're going to do for each of these graphs is you're going to go ahead and factor it completely. So here in the first one, again, the top, you may or may not need to use the AC method or whatever you happen to use for your factoring. Again, I'm done so many of these, I can just go ahead and look at it. So 3x plus 2 times x minus 3 over x minus 3 times x plus 1. Here for the g function, factors of negative 10 that add up to be positive 3. That's going to be plus 5 and minus 2. And then difference of squares on the bottom. If you're wondering, are we ever going to cancel out those common factors? Yes, but we first want to make sure that we understand exactly what it is they do. So the restricted values, x cannot be 3 or negative 1, and x cannot equal plus or minus 2. So your domain is everything but the restriction. So negative infinity to negative 1, negative 1 to 3, and then 3 to infinity. Compare that to negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. What are the zeros? If you forget, go back up to where it says your zeros. You're going to set the non-canceling factors of the numerator equal to 0. So here in the first one, the non-canceling factor would be 3x plus 2. And if you go ahead and solve, you're going to get negative 2/3. In the next one, the non-canceling factor is x plus 5. So that's going to give you an answer of negative 5. And then to find the y-intercept, again, at its core, you're setting x equal to 0. But really what you're doing is finding the ratio of the constant term on the top divided by the constant term on the bottom. So negative 6 divided by negative 3, that's going to give you a y-intercept of 0, positive 2. negative 10 divided by negative 4. That's going to give you a y-intercept of 5/2 or 2.5. So again, looked a little different today because I thought it was very important that you were able to keep all your notes organized. And again, because I had the graphs I wanted you to look at, I thought this would be a good way for you to take notes. So maybe we'll keep going this way, or maybe we'll switch it up. We'll see how it goes. But thanks very much, guys, for tuning in. You're going to go ahead and attempt homework 21 tonight. You can find that in the class notebook, and you should see that it follows a very similar format. So just refer to today's notes as needed.